This one is C12H16O2. It has 5 double bond equivalents. We have an aromatic ring over here, 5H, in the 7 to 8 region. That's going to be C6H5. We have a 1H over here. That's going to be a CH. We have a 4H here. Now the 4H is going to be two CH2s, but because they're under the same peak, we know that they must be related by some sort of symmetry. Over here we've got 6H, and that is going to be two CH3s. Now I just want to show you a little bit of a discussion here about situations where you have a 6H peak. Generally speaking, if you've got a single peak, a double peak, or a triple peak on the 6H, due to symmetry requirements, this is usually going to indicate that we have two CH3 groups in that situation. The only time when we have a situation where there's three CH2s is when we have 4 peaks in the 6H, under the 6H region. In all cases though, the groups are related by symmetry. Now we're almost done here. We've got a C, 2 O's and double bond equivalent. That means we've got a C double bond O and an oxygen. Everything counts down to 0, so these should be all the pieces. Now in this case the anchor's down here, so I have to put it down here. And now I have to figure out what else is going to go with what. Now what I know here is that we have a CH group, and the CH group has 5 peaks. That would indicate that it is adjacent to 4 hydrogens. Because we know we have two CH2 groups, and those two CH2 groups are related by symmetry because they're under the same peak, I'm going to posit that the CH is going to be adjacent to two CH2 groups. The other thing we know is that the CH3 groups have 3 peaks, which means they must be adjacent to two CH2 groups. That leaves us in a situation like this. So now we have a C double bond O and an O left over. I'm going to move this over a bit because the only way that we can, the only places we can put this, all these groups, is down here. But now we have to figure out which way it goes. Does it go this way, or does it go this way? Well, to answer that question, we can take a look at my discussion for ester groups here. And here's what we know. In an ester grouping, we have a situation here where the CH2 is directly bonded to the oxygen. We can see the CH2 is going to be at 4.0 ppm. And here the CH3 group is directly bonded to the C double bonded oxygen, and that's going to appear between 2 and 2.5 ppm. Looking at our situation, what we've got is a CH group at around 4.0 ppm, which would indicate that that is directly connected to the single bonded oxygen. So it's going to look like that. We can get another bit of a clue here by looking at the interaction of the C double bond O with the aromatic ring. What we notice about C double bond O's next to aromatic rings is when they're directly connected, it has the effect of splitting the aromatic ring into 2 peaks, and as those peaks are centered usually around 7.5 ppm. If it was the oxygen that was directly bonded to the aromatic ring, it would still split into 2 peaks, but the peaks would be centered at around 7 ppm. Looking at what we've got here, we've got 2 groups of peaks and they're centered at around 7.5, and that would indicate that we do have indeed a C double bond O directly connected to the aromatic ring.